Hey maths fans, inverse functions is the topic here. So what are we talking about with inverse functions? Well, inverse operations are add, subtract, times, divide. The inverse is kind of like the opposite. It's a way to undo the operation. So for example, if I take a number and I add 2, then the inverse is to subtract 2. Doesn't matter what that number is. If I put a 5 in here, 5 plus 2 is 7. The inverse of that, if I take 7 and I minus 2, I get back to where I started. So it's a way of getting back to where you started. It's the inverse, the opposite, to undo an operation. Inverse of times is divide. Inverse of divide is times. Inverse of square is square root. And they undo that operation. Okay, let's consider the function y equals 2x plus 3. That function y equals 2x plus 3. What am I doing to the input there? I'm taking an input, x, I'm multiplying it by 2, and then I'm adding 3. And that gives me the output of y. If I want to undo that, I want to do the inverse, I'm going to start here. The inverse of the plus 3 is subtract 3. The inverse of the times 2 is divide by 2. So if my input went here, then I would say, I would take x, take away 3, then I would divide by 2. And so this is the inverse function for this one. Okay? So we undo the operations. We invert them. Another way of sort of figuring out the inverse of something is to change the subject of an equation. So if we've got y equals 2x plus 3, if I make x the subject there, I would take away 3, then I would divide by 2, and so I would get x equals y minus 3 over 2. Now you'll notice that actually our inverse function, we swap the x and the y back around so that we have the same subject in both of them. So that's one way of finding the inverse, is to change the subject, then swap around your x and y. Right, let's look at what that means a bit graphically. So if a function maps x onto y, then its inverse is going to do the opposite. It's going to map y back to x. And this here is how we show an inverse function. This f minus 1x, that means the inverse function of f of x. So if we have the point x, y, that's on the graph y equals f of x, then the opposite point, or the swapped around point, y then x, must lie on the graph of the inverse function. I'll show you that graphically here. So we've got a couple of points here. Here is my line y equals f of x, and this is that line y equals 2x plus 3. You can see we've got a coordinate there at 1, 5. The x is 1, the y is 5. On my inverse function here, and this is that y equals x minus 3 over 2, we find that we have that coordinate swapped round. So if 1, 5 is on this line, on the inverse function we'll have 5, 1. If 2, 7 is on y equals f of x, 7, 2 is going to be on the line y equals the inverse of x. Okay. You might also have spotted that they are a reflection of each other. When I have the inverse function, it is reflection of y equals f of x in the line y equals x. So that line going through the middle there, going 1, 1, 2, 2, 3, 3, 4, 4, those are the coordinates of the line y equals x. It's a famous line, you should hopefully recognize it. That is my line of reflection to map y equals f of x onto y equals f minus 1 of x, the inverse function. It is a reflection in the line y equals x. Okay, moving on. So a function may or may not have an inverse function. If we remember back to our work with functions, a function can only have one output for every input. So it had to pass a vertical line test. When we're trying to invert something, it has to be a one-to-one function. So a function is one-to-one if every value of y, there is only one value of x. So every output needs to have only one input. If it is one-to-one, if we have a one-to-one relationship, then we do have an inverse. So we can say that this set of mappings here, it is a function because each input has one output, boom, boom, and it's also invertible because there is only one input for every output. If I look at this example, we have what we call a many-to-one mapping. So we have, and I think this is going to be squaring, so you can see when I square -1, I get 1. When I square 1, I get 1. So this is a many-to-one relationship. This is not invertible, and we'll show that graphically in a second. Because for something to be have an inverse, it needs to mean that every output must have only one input. So it has to first of all pass the vertical line test, and then this part is going to be determined using a horizontal line test. I'll show you that on some graphs now. So, one-to-one functions satisfy the horizontal line test and the vertical line test. So if we have this function, y equals f of x equals 2x plus 3, we need to make sure that that passes the horizontal line test. Well, is there only one place that this horizontal line is touching the purple line? Yep, all the way up. I can drag that forever. So this is a one-to-one function. For every output, for every y value, there is only one x value. Oops. For this second example, where we've got f of x equals x squared, if I drag this horizontal line, it's got two possible inputs for every output. And down here, doesn't matter. So you can see this black graph here is not passing the horizontal line test. It is not touching that horizontal line only once. Okay, it does not have an inverse function. The reason being that when we reflect that, we've now got two outputs for each input, which means it would fail the vertical line test, which means that's not a function, so the black line can't have an inverse. I hope that makes some sense. The basic thing is, drag a horizontal line across your graph, use a ruler, use a pencil, whatever. If it has two, so looking at the black line here, the black curve, if it touches that red line twice or more, it's not an invertible function. Let's look at an example question, bring all this together now. It's a lot of information. Let's unpick it. So, here we have a graph, y equals f of x. Explain why it is an invertible function. Well, for it to be invertible, it has to pass first of all, the vertical line test to show it's a function, then the horizontal line test to show it is an invertible function. So we could put that into two sentences. It is a function because a vertical line cuts through the graph at most once. If we get ourselves a vertical line here, and we get ourselves, a horizontal line there and a vertical line here, then as I drag those across my line here, it's passing this test. It's only crossing that at one place for all of that. And is it passing this test? Yeah. From there to there, it's only ever cutting through that line once. So it's a function because any vertical line cuts the graph at most once. Good. And it's invertible because any horizontal line crosses the graph once. If it passes those tests, it's an invertible function. And also, just think, can it be reflected in y equals x? So we're about to sketch the inverse. And if I can reflect that, then we've got an invertible graph. So, what I want to do to reflect this graph in here is look at some of these coordinates. We've got 3, 4 here. Well, we know that the inverse will have the opposite of that, 4, 3. So this is a coordinate on that line. Down here, minus 5, 2 will become 2 minus 5. So I'll go to 2 minus 5 is there. So I know that those are 2 points on the line, and I know they're joined by a curve, so mine are going to be joined by a curve something like that. It's not perfect, but this word sketch means I don't have to be perfect. Draw, we've got to be as exact as possible. Sketch, we would just put this on, and we would give all of the information that we've used here. So I've used that coordinate, I've used that coordinate, 2 minus 5, and I've got this dotted line, y equals x, just make a reference to that. And I think that's all the information we would need to sketch the graph of the inverse there. So take some coordinates, plot them so that we've got some fairly accurate positioning, and then draw in your line as good a reflection as you can get. Final part here, C, state the domain and range of y equals f of x and of our inverse function. Well, the domain is all the inputs, the x values. So we can say that the domain for f of x is going to be from here to here. We're going from minus 5, so we can say curly brackets, x, vertical line, x is between, x is between minus 5 and up to 3. So that's the domain of f of x. The range of f of x is y. And y can be, done it again, y can be between, what's my y values? From 2 up to 4. So I've got from 2, y can be up to 4. Now when we look at the inverse function, very interesting to note that we've kind of got a very similar pattern here. My domain is now going to be from 2 to 4, and you'll notice that the domain of my inverse function is the same as the range of my function. I'll try and say that again in plain language. There's my domain and range. So the domain of the inverse is equal to the range of f. The range of f of the inverse is equal to the domain of f. So there's my domain and range for f of x. So my f minus 1 x has domain, and we'll take it from here, but it's going to be the x values. So my x is going to be between 2 and 4. And for the range, it's going to be, I can just take it from there. I could look at the graph I had also, but very useful to be able to just take what it is in here, swap that for a y basically. So y is going to be between minus 5 and 3. Okay, so that would be how to solve that example question. That's the inverse of functions. Reflective in the line y equals x, make sure they're a one-to-one relationship by doing the horizontal line test. And the domain becomes the range becomes the domain. But you swap the x and the y around. I think that's about it. Thanks for listening. Bye.